And our speaker is Dr. Preet Singh.
I'm going to stick to how corrosivity of molten salt is affected and impurities may be participating. I'm using impurities as a loose word here. Anything which is not pure salt, in my view, from corrosion or materials point of view, is either intentionally or unintentionally added impurity. This work is compilation of a lot of work by my students. Again, my name is Preet Singh. I'm professor at School of Material Science and Engineering at Georgia Tech. Kevin Chan, who finished his PhD and is now at Kairos Power, has done a lot of this work I'm going to show. And currently, Krishna Murthy-Sankar and Casey Hansen, they are continuing some of the work on, especially on fly neck as well as on some chloride salts. If our salts were perfectly pure, thermodynamics tells us that at least the structural alloying elements like chromium, iron, cobalt, etc., they should not have thermodynamic tendency to corrode in perfectly pure salt, because gives free energy of formation for these fluorides of lithium, sodium, potassium, or beryllium, depending upon whether we are talking of fly neck or fly. They are much lower compared to most of the structural elements. So corrosion is attributed to impurities, as Nathaniel alluded to. So here's an example. If we have hydrogen fluoride with high activity, or activity of 1, in that case, at that type of situation, the redox potential, or in actual correct word, chemical potential of fluorine will be such that we can have chromium selectively dissolve or manganese selectively dissolve into the molten salt, whereas iron, cobalt, nickel, tungsten, moly, under these conditions may not be. So there are a number of other impurities. It's not just hydrogen fluoride. We can have direct or indirect effect of these impurities on redox, which I'm going to use more often than actually a real word of chemical potential of fluorine. So the redox potential is going to depend on concentration and type of impurities that are present. These can also continue to build due to leaks or process-related chemical changes in the system. So a typical, for example, hydrogen fluoride can then react with chromium selectively at the surface of this alloy, giving you chromium fluoride, which dissolves into the solution. And if there are impurities like nickel +2 or iron +2, typically fluorides of so-called noble alloying elements, they can also cause corrosion. For example, if nickel fluoride was there, that will pull chromium into the system. So again, depending upon if we actually really reduce those concentrations of or increase those concentrations of impurities, that will have big impact on how or which elements will be pulled into salt. So we want to keep our salt as reduced in terms of redox potential as possible. So again, when I talk about impurities, I'm talking about these unintentional or unintentionally added impurities, which can come from salt, or they can come from other operation-related activities, but they have direct impact on redox potential, and they directly participate in alloy corrosion. For example, the same reactions shown here. There are other impurities like lithium oxide, which may not directly react with alloy, but indirectly can impact, and I'll allude to that a little bit. Then there are intentionally added, but with unintentional consequences. So this is where I suppose it's related to first talk in this session on graphite, where we know that in MSR designs, graphite is going to be one of the major structural component. Intentional presence is actually also affecting corrosion of alloys. Some of the work at University of Wisconsin has shown that there can be direct galvanic effect. In fact, our work has shown that if you do tests in graphite crucible versus nickel crucible, corrosion can be different. Kevin's recent work has shown that you can actually form carbides because we are carrying out reactions at 600 to 700 degrees Celsius in MSR reactors. At that time, if graphite is present on alloy surface, you can actually have carbide formation at alloy surface or wherever metal, ions, and carbon is available. Then last impurity that I talk about, again, I'm using it as a loose term impurity. We sometimes can control redox potential by adding active metals depending upon salt. For example, in fly it will be beryllium, in fly neck it will be lithium, and in magnesium chloride, potassium chloride type of eutectic, it may be magnesium. We can control redox, mitigate corrosion, but we also need to keep this in mind that beryllium, lithium, and magnesium may be also reacting with alloy components. And that's the work that hasn't been published much, and there's some work that we have done and continuing at Oak Ridge as well. So I'll just show a little bit of that. So going through these impurities, the first one, metal fluoride. So what Kevin did in this case, that he intentionally added nickel fluoride to fly neck, different compositions, and we found that actually presence of nickel fluoride increases corrosion in general, but grain boundary attack actually increases. So again, you'll carry out this reaction where nickel will exchange with chromium, forming nickel chromium fluoride, which is soluble, and nickel on the surface. So if you actually have a lot of this nickel fluoride impurity, in fact, it can lead to very aggressive attack. In 100 hours at 700 degrees Celsius, this Hastelloy N lost grains from the surface because of intergranular attack. So you can see that grains just fall off because of aggressive attack. So obviously we hope that we will never have this amount of impurities, but what we are trying to do is understand under extreme cases what type of mechanisms or what type of degradation mechanisms can operate. Other impurity that we looked at was carbonate, and some salts do have carbonate impurities, but carbonates can also form because of other means. So in this set of experiments, fly neck was doped with different amounts of carbonate ions in there. Basically, lithium carbonate was added in fly neck. And this sample, this metal sample here, they could be different metals, pure metals, as well as alloys. Apart from carbonate, there is no other source of carbon. Crucible is nickel, and this sample is actually isolated from crucible because it's hanging from alumina ring in this crucible. So what we found that if you do tests without any carbonate, just in fly neck, on left-hand side you have attack on the surface, which is some intergranular attack on the surface, but mostly smooth cross-section when you cross-section that sample. Now, if you add carbonate, you can have this reaction here where lithium carbonate will react with iron, giving you lithium iron oxide and carbon at the surface. So when we take that type of exposed sample and section it, we see a carbon or carbon layer at the surface. And also, if you look at SEM at the surface, there are discrete particles. So we characterized those and found that those particles were actually pure carbon, and they show Raman spectra here of both D and G, peak for Raman for pure carbon, whereas surface also had some carbon, but mostly covered with carbides. We also did X-ray diffraction of this type of sample to find out if lithium iron oxide is possible, and the red peaks are for lithium iron oxide, and you can see the middle graph here is with fly neck alone, and it only has iron peaks, but as soon as we add carbonate in there, we start to see lithium iron oxide at the surface as well. So there is a reaction of carbonate with iron, and similarly there can be one with chromium for sure. Nickel is more immune to this type of reaction. Can carbonate actually be generated in fly neck? And answer, we wanted to find out that especially the concern that we had in mind at the beginning was that oxides can come from, for example, dissolution of native oxide from metal surface, or it can be some other impurities. So if you have those oxides, oxides can react at the operating temperature with carbon or graphite, which is present in MSR type of design, giving you carbonate ions in the solution or system. And these carbonate ions here, they can actually be transformed, or they can transfer carbon to metal surface, where it can get reduced to form elemental carbon, which is available now to the metal to form these metal carbides. Now, similarly, reaction can be where you have carbon already on graphite surface. You can actually transfer these soluble metals on to graphite surface and find that you have now metal carbides on graphite surface as well. So this can continue, and you don't have to have carbonate in your salt. You can actually produce carbonate by reaction of oxides with carbon, giving you this mechanism that that we have proposed and shown. To prove that this is possible, we took some fly neck, and what you see here are Raman spectra. So if you take just fly neck, this is Raman peak or Raman signal. If you add simply lithium oxide in there, you still don't see any big change or big Raman peak. But if you now add graphite powder along with lithium oxide, instead of showing peak for graphite, you actually see a peak for carbonate. So lithium oxide does react with graphite, giving you lithium carbonate, which is soluble in solution. In these tests, we didn't have any metal exposed. These were done in nickel, no other reactive metal. And if we just directly add lithium carbonate directly, that peak is exactly the way it is for if you add lithium oxide and graphite together. So with that proof that yes, we can form carbonates with reaction, we wanted to find out what is minimum amount of oxide that is required before you actually start to see this carbonate. And we found that as you keep on increasing amount of oxide in the fly neck, so in this case we didn't add carbonate because we wanted to see if carbon can be transported from graphite to molybdenum sample, which are totally isolated electrically. They are farther apart, they're about 10 millimeter apart from each other in this crucible. So we were adding oxide so that carbonate could form on graphite surface and get transferred to the metal surface. In this case, metal was molybdenum because it forms molycarbide. Yes, we actually saw carbonate peaks in the fly neck where tests were done, especially when we actually increase our concentration of oxide significantly. We tested both Raman as well as total inorganic carbon in fly neck, and that inorganic carbon was in the form of carbonate. And you can see that carbonate peak, which is shown here. In this case, carbon can be transported from graphite to metal surface just by impurities. And for example, here, these oxides can form not just carbonate, but there can be other constituents like carbon dioxide or carbon monoxide. And they will transport carbon from graphite surface through molten fluoride to metal surface because of their driving force, where carbides can form on the surface here. Carbon monoxide or carbon dioxide or carbonate, they can actually convert depending upon oxidation potential and oxide concentrations. But main thing is that on metal surface, you can transport carbon, which is this metal may be totally away from graphite or electrically totally isolated, but through fluoride salts, this carbonate formation or carbon dioxide or carbon monoxide formation can lead to transportation of carbon from graphite surface to metal surface. And of course, you can form metal carbide on graphite because of corrosion reaction. Work at Wisconsin, University of Wisconsin has consistently shown, and our work has also corroborated the same results, that if you do tests in graphite crucible, corrosion, in this case it's 316 crucible versus graphite crucible, you can see corrosion rates given in terms of depth of attack, they are much deeper in graphite. Again, this is work by Zhang from, again, University of Wisconsin, nickel crucible versus graphite crucible, Hestloy versus Inconel 800H. Corrosion rate typically are higher for graphite. So corrosion can be increased if there is any graphite available at or near metal surface. But we wanted to see if graphite eventually can actually have other unintended consequences as well. So if you look at Gibbs free energy of formation of carbides, we find that from alloying elements, chromium, tungsten, moly, they readily form carbides, whereas nickel and iron are relatively, nickel especially is immune, but iron carbide driving force is more positive under conditions that we consider. We took chromium, we actually carburized it in gaseous form using propane and hydrogen mixture. And we carburized for different time periods and used that carburized or chromium carbide layered chromium sample to test for its corrosivity or corrosion tendency in fly neck at 700 degrees Celsius. This sample here is for when there is no carbide on the surface. As we increase carburization, corrosion rate measured in terms of mass loss decreases significantly, which basically shows that chromium carbide is acting as a barrier layer. So we did a lot of other work on alloys as well, and what we find that yes, corrosion rate eventually can decrease if you actually bind a lot of chromium with this carbon at the surface. So chromium carbide lowers the activity of chromium. So that is one factor which can actually decrease corrosion rate, because now driving force is lower because of activity of chromium available for reaction with fluoride has gone down. But also carbides can form a barrier film, but for that you have to have a continuous film or alloying element which is in large proportions. The last impurity that I want to talk about is the active metal that we add to control redox. So again, I'm calling it as impurity, but really it can be a good impurity or it can be bad depending upon what we are looking for. These tests were done, or data I'm showing is in chloride salts. If we don't have any magnesium added, just eutectic mixture of potassium chloride, magnesium chloride, and we do some tests with alloys, for example, Haynes 244, Hestloy N 316, and Inconel 625. The red bars are surface chromium content measured by XRF, X-ray fluorescence technique. And then the green ones are after test was done or after the samples were exposed to this chloride eutectic at 700 degrees Celsius for 100 hours. And you can see that Haynes 244 and Hestloy N behave exactly in the same way. They have similar amounts of chromium, but after test, there is similar amount of decrease in chromium content from the surface. Now 316 and Inconel 625 have higher amounts of chromium to start with, and the percentage ratio or percentage decrease in chromium content is significant. If you look at that sample of 316H, which was exposed to chloride salt, you see about 180 microns of intergranular attack in 100 hours in this particular salt. But as soon as you start to add magnesium, and if you add magnesium significant amount, you actually stop that corrosion almost completely. There's a very narrow zone of about 2 micron where you still have some chromium depletion. The problem with that is that magnesium, if it's in excess, can also react with alloying element nickel, and it can form magnesium nickel intermetallics depending upon how much of magnesium is there. It can be MgNi2 or Mg2Ni. So to test that, we actually looked at our nickel 200 sample, which is basically pure nickel, and looked at cross section, and after exposure with excess magnesium present, we actually see a dual layer. The inner layer, which is shown here in SEM, was actually rich in nickel because it's closer to nickel 200, and outer layer is rich in magnesium. So we got both MgNi2 and Mg2Ni in this sample. What can be problem is that if this happens on grain boundaries in the alloy, that can cause embrittlement. So we wanted to make sure that we can actually control corrosion, but not have nickel intermetallics, nickel magnesium intermetallics. We basically looked at various concentrations and found that you can optimize where you can actually reduce corrosion and not have nickel intermetallics form. So one has to be aware of that, and we confirmed that using X-ray refraction, and you can actually optimize how much excess elements can be added. So other concern was that fly will do the same thing if we add beryllium in there. So that's where Dr. Jim Kaiser and his team at Oak Ridge, as part of our NEUP project, is actually right now doing these tests for fly as well. So I think with that, I'm going to stop, but impurities are very important. Oxide impurities do not register as much in fluoride potential, but they can have indirect consequences. When we are using redox potential, depending upon how we use it, if we actually have active metal addition, we have to be mindful of their reaction with alloying elements. With that, I'm going to stop. I want to acknowledge my students, research collaborators from Oak Ridge as well as Sandia National Lab, Jim Kaiser, Kevin Robb, and also technical ideas and support by Dr. Holcomb and Dr. Qualls. I want to acknowledge NEUP and Sandia for funding.
Thank you for your attention to this session.